All right. An alternative hypothesis, which is denoted as H sub 1. Okay, whether we're testing a population mean or proportion or a standard deviation, the symbols for the alternative hypothesis are always going to be strictly a greater than symbol, or it could be a strictly less than symbol, or it could be a not equal to symbol. You got to be one of those. Okay. All right. So, knowing that this must be the case greatly aids our ability to establish our hypotheses for testing purposes. So the alternative hypothesis, ladies and gentlemen, is usually the claim that we are hoping to prove. Sometimes it is referred to as a result as a research hypothesis. Okay. So again, when we conduct hypothesis testing, we're going to have two hypotheses, a null hypothesis and an alternative hypothesis. The null hypothesis is denoted as H sub 0. The alternative is H sub 1. All right, hold on a second. Something's wrong. Okay, here we go. When we conduct hypothesis testing, we can conduct either a two-tailed test or a one-tailed test. A researcher is concerned that a new medication might change the pulse rate of a patient. Suppose the mean pulse rate for the population under study is 82 beats per minute. The researcher tests to see if the mean pulse rate of the patients who get the new medication is no longer 82 beats per minute. Therefore, their null hypothesis is going to say that the mean heart rate of all people out there in the population is equal to 82. And the alternative hypothesis would state that the mean heart rate is not equal to 82 beats per minute. Now, if we're the researcher coming up with this new drug, and we make a bold statement of saying our new drug changes the heartbeat, and we're hoping to prove that the alternative hypothesis is true, because the alternative hypothesis is saying that the mean heartbeat rate is not 82 beats per minute. This would be called a two-tailed test, because we are testing to see if the mean is either greater than or less than some value. In other words, we're testing to see if the mean is equal versus not equal to a value. We can also use a two-tailed test for testing proportions. Okay. Here's an example. 10% of all people are left-handed. Suppose we want to see if certain subpopulation has a different proportion of left-handed people. Then we would be testing these hypotheses, the null of which would say that the population proportion of left-handed people would be 10% versus the alternative statement that says population proportion of left-handed people is not equal to 10%. All right, so when your alternative hypothesis has a not equal to symbol, then we call this a two-tailed test. And you'll see why. This is called a two-tailed test. If your alternative hypothesis, on the other hand, has a less than symbol, or your alternative hypothesis has a strictly greater than symbol, these are called one-tailed tests. And specifically, if your alternative hypothesis statement is a less than symbol, this is called a lower tail test. Lower tail. If it has a strictly greater than symbol, it's called an upper tail test. For reasons of which will become clear in the near future, this is called an upper tail test. All right, so when we conduct hypothesis testing, it's either going to be a two-tail or a one-tail test. So these symbols can indicate to you just at a glance as to what type of test is being conducted. All right. All right, this would be an example of a right-tailed test or an upper tail test. When they say right-tail test, that's another name for upper tail test. An engineer is trying to increase the lifespan of an electric motor. The old motor lasted 5 years on average before failing. The engineer has a new motor and wants to know if the average lifespan of the new motor is larger than the average lifespan of the old motor. So the alternative hypothesis would be stating that the mean lifespan of this new motor we created exceeds 5 years. The null hypothesis says that the mean lifetime of this new motor we created is equal to 5 years. These would be the hypotheses that would be tested for this particular claim here. The engineer only cares if the average increases, and an alternative hypothesis of if the engineer only cares if the average increases, and an alternative hypothesis of mu not equal to 5 would be satisfied if the new motor had a shorter lifespan as well. So it really depends on what they want to test. If they want to just test to see if the new motor's lifespan on average is different than 5 years, then you would have the alternative hypothesis statement looking like this, in which case it would be a two-tail test. But if you want to test to see if your new motor that is created, if its average lifespan exceeds the lifespan of the old motor, then that would be an upper tail or right tail test, and your alternative hypothesis statement would have to take on this complexion. Okay. And ladies and gentlemen, we can also use one and two tail tests for testing for population proportion. Suppose we want to see if a ballot proposition will pass. We want to see if the proportion of voters who support it is greater than 50%. If that's the case, this would be our alternative hypothesis statement. That is stating that the population proportion of voters who support this resolution is greater than 50%, as opposed to the null hypothesis that says that it is equal to 50%. Okay, this would be an upper tail test or a right tail test because of our alternative hypothesis statement here. All right, if we're conducting a left tail test, sometimes referred to as a lower tail test, then we would want the less than symbol to be evident in our alternative hypothesis statement. So if you see an alternative hypothesis looking like this, then this would be a lower tail test or a left tail test. An example would be a grocery store is trying to streamline its checkout process to reduce the average length of time customers wait to ring up their purchases. Currently, customers wait on average of 17 minutes to check out, but the store hopes the new procedure will speed things up. The null hypothesis, therefore, will be saying that the mean wait time of all customers is equal to 17 minutes, as opposed to the alternative hypothesis, which would be our claim or our hunch or our gut feeling or our hope, would say that the mean wait time of all customers would be less than 17 minutes. If, on the other hand, the store owners just wanted to check and see if the mean wait time is different than 17 minutes, then they would revert back to a two-tailed test, and their alternative hypothesis statement would be stating this about the mean wait time. Population proportion testing can also make use of a left tail or lower tail test. Suppose that we want to see if fewer than 19% of people will respond to a phone survey. If that's the case, our alternative hypothesis would look like this then, where we have a less than symbol. That's suggesting we have a left tail or lower tail test. And the null hypothesis would be the complementary statement, if you will, which is saying the population proportion is equal to 0.19. So again, it's the alternative hypothesis that basically dictates what type of test we're conducting, the symbol that's used. All right. Now, when we conduct hypothesis testing, ladies and gentlemen, we're going to have to use probability theory to help us out. And we're either going to have to use the continuous normal probability distribution, okay, or we might use the continuous t probability distribution to help us make a decision on our hypotheses. Suppose our researcher studying heart rates calculates the sample mean of the heart rates of the patients in the study. Recall that the sample mean will vary about the population mean, and that the distribution of this variation is approximately normally distributed when the sample size is at least size 30, according to the central limit theorem. Therefore, if the null hypothesis that the population mean heart rate was 82 beats per minute is true, the sample mean is almost certainly not going to beat 82. On the other hand, if the null hypothesis is false and the population mean is not 82, it is also likely that the sample mean will not be close to 82. If the sample mean were 83, that is close enough to 82 to probably be due to chance. On the other hand, if like the sample mean was like 90 beats per minute, then you can see that that is significantly different than the purported population mean heart rate of 82. And therefore, since we have such a deviance between the sample heart rate and the purported population heart rate, we would be inclined to think that the null hypothesis is false. And we would probably, in that case, opt for the alternative hypothesis as being a true statement. But the thing is this, ladies and gentlemen, if we say that in our null hypothesis, if the mean heart rate of all people out there is 82 beats per minute, and we compute a sample mean heart rate, we reach into the parent population, pull out a sample of size at least 30, and we compute a mean heart rate of like 90, or like a mean heart rate of 83 or 84, 85 or 87, or maybe a mean heart rate of 79 or 77 or 76. How do we know which mean heart rate would be the cutoff value for deciding or opting for accepting an alternative hypothesis as being a true statement and rejecting the null hypothesis as being a true statement? How do we know what that value is? I mean, we don't know. Well, the only way to know that is to conduct what is called formal hypothesis testing and use probability theory to help us make that decision. Just like when we're building confidence intervals, all right, if we don't know a population mean, a first rough guesstimate is to use as a point estimate the sample mean. But remember I said that if you reach into a parent population and pull out a sample of size, let's say 50, compute the mean, is that sample mean going to be the same as if you were to reach in and pull out another sample of size 50 and compute that sample mean? The answer is no. In fact, there could be hundreds of thousands or millions of samples of size 50 you could reach into the parent population, pull out, and each one of those sample means would be different. So how would we know which sample mean is the most accurate assessment as to what the unknown population mean value is? Well, we would not know, and we would not know until we build a confidence interval, because the confidence interval enables us to establish the level of confidence so that we have some idea as to how close or how far off our sample mean is from the actual unknown population mean. Same thing in hypothesis testing. Just because we reach in and pull out one sample and compute its mean, all right, we have no measure as to how accurate or inaccurate this sample mean is compared to the unknown population mean. That's just one sample. I mean, we could maybe pull out maybe hundreds of thousands or millions of samples from this population, and each one would have a different mean. So, ladies and gentlemen, in order to make an accurate decision on what we're going to do with these hypotheses, we're testing for an unknown population parameter, we have to use formal hypothesis testing. Okay. And hypothesis testing does make use of probability theory and ultimately the central limit theorem that we looked at in the past. Now, when we conduct a hypothesis test, we reach into the parent population. Let's say we're testing for an unknown population mean. We reach into the parent population and we pull out a sample and we compute the sample mean. Then we have to use this sample mean to compute what is called a test statistic value. And you'll see next week when we actually start conducting hypothesis testing for an unknown population mean that this test statistic value also involves our critical Z value or critical T value, depending upon what distribution we use, depending upon whether we do or do not know the population standard deviation. And it also makes use of the standard error of the sampling distribution of our sample means. Okay. So this test statistic is going to enable us to ultimately make a decision on whether we have enough evidence to reject our null hypothesis and opt for the alternative hypothesis, or we do not have enough evidence to reject our null hypothesis. Okay. Now, all of this is pretty much as clear as mud in our minds right now, because all we're seeing is a bunch of words here. The only way you really understand hypothesis testing is by seeing examples, okay? And by seeing examples, how they're done, then it starts to all come together and make sense. So don't judge this lecture today, which is a very general introduction to hypothesis testing. Don't use this lecture to generalize as to your success or failure that you think you're going to experience when conducting hypothesis testing. Okay, it gets better. It gets a lot better, all right, with examples. Trust you me. Because I was in your position at one time when I was first introduced to all this jargon, and it really made no sense to me as to what any of this meant. Okay. All right. So, ladies and gentlemen, when we conduct hypothesis testing, there will be 4 possible outcomes that could occur. One possible outcome is, suppose that the null hypothesis is actually true, and we fail to reject the null hypothesis. Is that a good thing or a bad thing? If the null hypothesis was a true statement and sample evidence shows us to not reject the null hypothesis, would that be a good decision or a bad decision? Are we accepting truth in that case, or are we rejecting truth? Well, since the null hypothesis is true and we fail to reject it, that indicates that we're not rejecting truth. And that's a correct decision. That would be a correct decision. Another possibility could be, suppose that the null hypothesis is false. Well, if the null hypothesis is false, then obviously to make a correct decision, we would want to reject the null hypothesis, reject something that's false. Suppose that sample evidence shows us that we are actually able to reject the null hypothesis. Would this be a correct decision? The answer is yes. That would be a correct decision because we're rejecting something that's false. That's a good thing. There's another possibility. Possibility number 3. Suppose that the null hypothesis is true. But suppose that sample evidence suggests that we are to reject the null hypothesis. Is that a correct decision? If we reject something that's true? No, that's not a correct decision. All right. If that happens, ladies and gentlemen, we commit a very serious error when conducting hypothesis testing. It's called a type 1 error. A type 1 error is the worst mistake or error you can fathom or commit when conducting hypothesis testing. That is when you reject the null hypothesis when in fact it's a true statement. That's a bad thing. But you know, the beauty of hypothesis testing is we can control the amount of type 1 error that we risk in making such a decision. We are the ones that can control that risk. And that's a good thing. There's one other possibility. Suppose the null hypothesis is false, but we fail to reject it. Well, in that situation, we commit what's called a type 2 error, failing to reject something that's false. Now, a type 2 error is not as serious as a type 1 error. Normally, we don't analyze in great depth or concern ourselves in great depth with a type 2 error. Normally, it's a type 1 error that we are concerned with always when conducting hypothesis testing. Okay, so those are the 4 possible scenarios that could occur when you conduct hypothesis testing. All right, when we conduct hypothesis testing, we, as the researcher, sets what's called a level of significance. And this level of significance is a threshold value that is used for deciding whether or not to reject the null hypothesis. And this level of significance that we set is called a probability. Okay, it's the probability of committing a type 1 error. And ladies and gentlemen, the probability of committing a type 1 error is equal to, they use alpha to represent the level of significance when conducting hypothesis testing. And like I said, committing a type 1 error is the worst thing that could happen to you when you conduct hypothesis testing. The normal levels of significance that we test at when conducting hypothesis testing is usually the 10% level, the 5% level, or the 1% level. That's not to say that you could not, conduct a hypothesis test at maybe 8% or maybe at like 4% or 6% or something. But normally we test at 10%, 5%, or 1%. Just like when we were building confidence intervals, we normally constructed those confidence intervals with levels of confidence that were usually 90% or 95% or 99%. Okay. All right. Now, the probability of committing a type 1 error is actually a conditional probability. And let's see if I can print this out on this paper here. This is very important, so I want to type it out if I can. Okay, so the probability of committing a type 1 error this probability is a conditional probability. It's the probability that our test statistic obtained from our sample is as extreme or more extreme, okay, as the one we actually obtained, given that, so there's that vertical bar, given that the null hypothesis is true. So that's really what the probability of committing a type 1 error is. It's a conditional probability. Given that our null hypothesis is actually true, it is the probability that our test statistic that we've actually compute is as extreme or more extreme. And this conditional probability here is one method, or the probability of making a type 1 error is another way of determining what we're going to do with our hypotheses, whether we're going to reject or accept a null hypothesis. Okay. Now, we will see that there's an inevitable trade-off, just like there was when we could build a confidence interval in our level of confidence versus precision. Because some of you are saying, well, if alpha is the probability of committing a type 1 error, then why wouldn't we want to decrease this level of significance to a very small level, so that we don't have to have a risk of committing a type 1 error here. But you'll see that when we reduce the level of alpha way down, okay, then that's going to enable us, or it's going to force us to, in all cases, just about all cases, accept a null hypothesis as being a truthful statement. The problem with that, ladies and gentlemen, is that in such a situation where our level of significance alpha is very, very small, that would lend credence to the fact that our null hypothesis is not true, in which case we should be rejecting it. But you'll see that when alpha is set to a very low level, our rejection regions decrease in size and our acceptance region of the null hypothesis increases in size. And so that we would be ultimately accepting a null hypothesis that in fact is probably false. Okay. So it's a trade-off. When you lower your level of significance, you are more often than not forced into rejecting your null hypothesis, in most cases, when in fact it's probably false. If you increase your level of significance, you're increasing the size of your rejection region, which means you would be forced in most cases to reject your null hypothesis. Okay. But the problem with that is you stand a larger chance of committing a type 1 error. So how do you have your cake and ice cream and eat them both? Well, you increase the size of your sample, because by increasing the size of your sample, you're going to decrease your margin of error. And your margin of error is used, like I said, when computing a test statistic value. All right. So the key is the larger sample you choose, the better off your results are always going to be whenever you're conducting any sort of inferential statistics. So always try to choose as large of a sample as possible. Okay, hold on a second. So once a level of significance has been selected, a critical value is then computed, depending upon what distribution we use. If we use our normal distribution, we use the inverse norm function on our calculator to find the critical z value. If we use the student t distribution, we have to use the inverse t function or the t table in the back of your book to find what your critical t values are. These critical values, critical z or t values that we compute, separate the possible values of the test statistic into two regions. One region is called the rejection region, or sometimes they refer to it as the critical region. It is the range of test statistics for which the null hypothesis should be rejected. If your test statistic is in the critical region or falls in the rejection region, then we will conclude that the null hypothesis is false, and we will reject it. We also form what's called a non-rejection region with our critical z or t values, sometimes referred to as the non-critical region. It is the rest of the possible values of the test statistic. A test statistic that falls in the non-rejection region would then give us reason to not reject the null hypothesis. Okay. All right. Okay. A one-tailed test can either be a left tail test or lower tail test, or it could be a right tail test or upper tail test. And if we are conducting a upper tail test or a right tail test, our rejection region is going to be in the upper tail of the standard normal probability distribution or the student t distribution, depending upon what test we're conducting. That's why we call it an upper tail test, because the rejection region will be only in the upper tail of the normal distribution or t distribution. Okay, and let's see here. For example, suppose we want to do a right-tailed z-test. Z-test means we're going to be using the standard normal distribution with a level of significance of 1%. In other words, we stand a 1% chance of committing a type 1 error. Then the critical value will be a z-score such that 1% of the area of the standard normal distribution will be to the right of our z-score. And 99% of the area will be to the left of the z-score. And therefore, ladies and gentlemen, how would we find that critical z-value? Well, we use our calculator and we use our inverse norm function. So if we're testing at 1%, 1% level of significance, we would go get our inverse norm function, and the area to the left of the critical z-value that we are trying to find would be 99%, 0.99. It's got to always be the area to the left of the critical z-value. That's the way our calculator function works. The mean of the standard normal distribution is 0, and the standard deviation is 1. And we discover that we do get about 2.33. So that would be the critical z-value for a hypothesis test. If you're testing at 1% level of significance, that means the area in the upper tail of the standard normal distribution would be 1% of the entire area of the curve, and then 99% of the area would be below that. Okay, so that's how we find our critical z-value for an upper tail or a right tail test. A left tail test is done in a similar way. So, ladies and gentlemen, if we were conducting a lower tail hypothesis test and we're testing at 1%, now the rejection region will be in the lower tail of the standard normal distribution, and its area will be 0.01. In that case, the critical z-value will be not positive 2.33, but negative 2.33. Okay. So the rejection region will be in the lower tail of the standard normal distribution, and the do not reject or the acceptance region of the null hypothesis will be to the right of that negative 2.33. And keep in mind that how do we know which is which? If we're conducting an upper tail test, our alternative hypothesis will have a greater than symbol. If we're conducting a lower tail test or left tail test, our alternative hypothesis symbol will be a less than symbol. Okay. What if, however, we are conducting a two-tailed test? A two-tailed test is going to have two critical regions or two rejection regions. And the region in between those two rejection regions will be the acceptance of the null hypothesis region. So suppose that we have a two-tailed hypothesis test and we're testing at 1%. Our level of significance is 1%. Well, that means this 1% is going to be equally allocated to the lower rejection region and the upper rejection region. So the size of the lower and upper rejection region is only going to be 0.005. So that's only 5/1000ths of the area of the entire curve, allocated equally to the lower and upper rejection region. And again, we would know that it's a two-tailed test if our alternative hypothesis statement has not equal to symbol. Not equal to symbol means two-tailed test. Okay. Suppose we're testing at 1% level of significance. So this is the probability of committing a type 1 error. And we want to find the critical z-values. So how would we do that? Well, we bring up our calculator. And we're going to use the inverse norm function again. Now, what would be the area to the left of the critical z-value? I'm going to use the lower tail critical z-value. The area would be 0.005. The mean and standard deviation of the standard normal distribution is 0 and 1 respectively. And that would give you your critical z-value of negative 2.58. And the upper tail critical z-value would be positive 2.58 by symmetry. So any test statistic that falls between negative 2.58 and positive 2.58 would suggest that we would not reject our null hypothesis. We would accept our null hypothesis. If, on the other hand, we get a test statistic that is greater than 2.58 or less than negative 2.58, then that would be a reason or evidence to suggest that we would want to reject our null hypothesis and opt for the alternative hypothesis as being the truthful statement. Okay. And this is just showing you how we got the 2.58 for the critical z-values if you're conducting a two-tailed test at a 1% level of significance. All right. So in the event that we were conducting a lower tail test or a left tail test, notice your hypotheses, if you're testing for a population mean mu, would look like this. Your alternative, your null hypothesis would be saying that the population mean is equal to some value, whereas your alternative hypothesis says the population mean is less than that value. This would warrant that we conduct a lower tail test or a left tail test. In which case, the rejection of the null hypothesis region will fall in the lower tail of the standard normal probability distribution. In which case, the critical z-value, which is going to be this value on the horizontal axis that separates the rejection region in the lower tail from the upper area of the standard normal distribution, which is called the acceptance region of the null hypothesis, or the do not reject region. Common critical z-values for such a lower tail test, if we're testing at 10%, our critical z-value would be negative 1.28. If we're testing at 5% level of significance, the critical z-value would be negative 1.65. If we're testing at 1%, the critical z-value would be negative 2.33. All of these can easily be found using your inverse norm function. So like for the first one, if you have a level of significance of 10%, you go to your inverse norm function and you type in the area to the left of your critical z-value as being 0.10. And you'll find that you get negative 1.28. If your level of significance is 5%, you type in the area to the left of the z-value is 0.05. And you get negative 1.65, et cetera, et cetera. Now, this would be an upper tail test. If your hypotheses look like this indicates that we're conducting upper tail or right tail hypothesis test. If your null hypothesis says your population mean is equal to some value versus the alternative says your population mean is greater than that value, this is an upper tail test. Therefore, your rejection region of the null hypothesis will be found in the upper tail of the standard normal distribution. And its size is going to be equal to alpha, your level of significance. So if you test at 10%, the size of this rejection region will be 10%. That means the size of the do not reject region would be 90%. To find the critical z-value that separates the rejection from the acceptance region, we would use our inverse norm function. And we would type in an area of 0.10. Well, actually, we should not type in 0.10 in that case. What should we type in? What area is to the left of our critical z-value? If we're testing at 10%. It wouldn't be 0.10, it would be what? 0.90, correct? Because 90% of the curve lies to the left of our critical z-value in that case. So in that case, we would use our inverse norm function. And we would type in 0.90. And we get 1.28 would be a critical z-value. If you're testing a significance level of 5%, you would type in 0.95 for being the area to the left of your critical z-value, because your rejection region would be of size 5% or 0.05. And you get 1.65. If you're testing at 1% level of significance, then you type an area of 0.99, because the area and size of your upper tail rejection region would only be 1%. And you'd get a critical z-value of 2.33. If you're conducting a two-tailed test and you're testing at 10%, how would you find your critical z-values? And by the way, how would you even know, looking at your hypotheses, whether you're conducting a two-tailed test? This is what your hypotheses would look like. Your null hypothesis says the mean is equal to some value, and the alternative hypothesis says the unknown population mean is not equal to that value. Because you have not equal to for your symbol in your alternative hypothesis statement, that's a two-tailed test. So if you're testing at 10%, that means that 10% divided by 2, or 5%, would have to be the area of both the lower tail rejection region and the upper tail rejection region. And to find the critical z-values, you'd use your inverse norm function, and to find this one down here, you would type in an area of 0.05, and you would discover that you get negative 1.65. By symmetry, then, your upper tail critical z-value would be positive 1.65 up here. If you're testing at 5%, then 2.5% of the area is allocated equally to the lower and upper tail rejection region, in which case typing in 0.025 for the area to the left of your critical z-value would give you a critical z-value of negative 1.96. And by symmetry, your upper tail critical z-value would be positive 1.96. Testing at 1%, and 0.005 would be the area of your lower and upper tail rejection regions. And you type in 0.005 and get a critical z-value of negative 2.58. And by symmetry, your upper tail rejection critical value would be 2.58. So when you conduct hypothesis testing, it's either going to be one of these three things, either a lower tail test, upper tail test, or two-tail test. It's got to be one of those three. And that's also for testing for a population proportion, not just for a population mean. All right, so ladies and gentlemen, there are 5 steps when we conduct hypothesis testing. 5 steps. Step number 1, we need to clearly state what hypotheses we are testing. You need to clearly state your null hypothesis, and you need to clearly state what your alternative hypothesis is. Step number 2, we then want to find the critical value or values for our rejection versus acceptance region of our hypothesis test. And that's going to depend upon whether you're conducting a one-tailed test or two-tailed test as to how many rejection regions you're going to have, okay? And also the size of your rejection regions. Now, What they're leaving out here, ladies and gentlemen, in step number 2 is what you have to do is you also have to set the level of significance that you want to test at. So you have to set alpha's value. Are you going to test at 10%? You're going to test at 5%? Or are you going to test at 1%? You need to know what alpha is so that you can determine what your critical Z values or T values are going to be. Okay? So make sure that you make note of that. So step 2 is you have to set your level of significance. That then will enable you to compute your critical Z or T values. Step number 3 is the step where we reach into the parent population and pull out a good sample. And we use that sample result to compute what is called a test statistic value. Step number 4 is then we're going to use our test statistic and we're going to compare our test statistic with our critical Z or T values to see in what region our test statistic falls. If it falls in the rejection region, we will reject the null hypothesis. If it falls in the acceptance or do not reject region, we will not reject the null hypothesis. And step number 4 is illustrating that step. We will make a decision as to whether or not we are going to reject or accept the null hypothesis. And then step number 5 is, in plain English, state your conclusion. Okay. And this last step is very important here. Ladies and gentlemen, let's say you're having to give a report to company employees and they don't know anything about hypothesis testing or statistics whatsoever. If you just come into the boardroom there and you start spouting off, well, sample evidence shows that I was able to reject the null hypothesis and only stand a 5% chance of committing a type 1 error. All of that, what you just said, would go right over their head. They wouldn't even have a clue what you just said. No, what you have to do is you have to water down your summary or conclusion in plain, simple English so that a layperson can understand what it is you're trying to say. Saying something like this would make more sense. Well, according to sample evidence, ladies and gentlemen, I have found that the mean diameter of all the ball bearings our machines are cranking out is less than 0.02 millimeters. Even a layperson could appreciate and understand what you just said there. Okay? So that your conclusion, your summary is critical in that you understand it clearly, but more importantly, that you're able to word it in such a way that a normal, ordinary human being can understand what you're talking about that doesn't know anything about hypothesis testing. Okay? All right. So the way that I've shown you on the previous slides to make a decision as to whether we're going to reject or accept the null hypothesis, that method is called the critical value method or the critical Z or T method. But ladies and gentlemen, normally we conduct hypothesis testing using our calculator, our TI-84, in which case we conduct what is called a p-value hypothesis test, or we use the p-value method for making a decision on what we're going to do with our null hypothesis, whether we're going to accept it or reject it. Okay. And a p-value, ladies and gentlemen, is a probability. It's a probability. And when you conduct a hypothesis test on your calculator reports what's called a p-value. Right? For example, suppose we are doing a right-tailed z-test for a population mean, where these are our hypotheses that we're testing. The null hypothesis that says the population mean is equal to 50 versus the alternative that says no, the population mean is greater than 50. Suppose we get a sample mean of 52. The p-value would be the probability of getting a sample mean equal to or larger than 52, Because the larger the test statistic value is, the more likely we are to reject the null hypothesis. Kind of makes sense. Because the larger our test statistic value is, lends more credence to us wanting to reject the null hypothesis, because this is a one-tailed or upper tail test. You see that? So our rejection region is going to be in the upper tail of the standard normal distribution. So if we get a test statistic that is larger than our critical z value, then that's going to push our test statistic into the upper tail rejection region, which means that we are going to more likely opt for rejecting the null hypothesis and going with the alternative hypothesis as being a truthful statement. Okay. And this p-value can give us an idea as to whether or not we're going to accept or reject the null hypothesis. And the way it works is this, and I've been working on this rhyme here for quite some time. This is what you need to remember here. For p small, we reject the null. See, that rhymes. It's easy to remember. For p small, we reject the null. So for a small p-value, we reject the null hypothesis. So obviously, for a large p-value, we what? We accept the null hypothesis. Well, how large is large and how small is small for a p-value to make this call? Well, the way it works is this way here. If our level of significance alpha is greater than our p-value, if that's the case, then we reject the null hypothesis. We reject the null hypothesis. And we only stand a probability of committing a type 1 error of being equal to alpha. If, on the other hand, your level of significance that you, the researcher, sets, remember, we are the ones that determine what level we're going to test at, 5%, 10%, 1%. If your level of significance alpha is less than your p-value, then we say our p-value is too big, in which case we must accept our null hypothesis. We cannot reject the null hypothesis, which means we accept the null hypothesis. Okay. So it really depends on what your p-value is and how it relates to your level of significance. If your p-value is less than your level of significance, you can reject your null hypothesis at that level of significance. If it's not, then you must accept your null hypothesis. You cannot reject it. So the p-value method basically circumvents us from having to find critical z or t values and then seeing in what region our test statistic falls in. So it's more automated by using your calculator, where you don't have to actually, determine your rejection acceptance region. That's called the p-value method. And we'll show you how that works on the calculator when we get into actual examples. Okay. All right, so let's just go to our textbook now and see if we can get into trouble. Oh, let's see here. I think I got timed out. Okay. I'm going to walk ourselves through a couple of these problems here. You'll see how they're done. And it's really through examples, ladies and gentlemen, where this starts to come into focus, this whole concept of hypothesis testing. Because like I said, right now, it's probably pretty nebulous in your mind as to what's going on. But it all starts to come together with examples. All right. So section 8.1. Steps in hypothesis testing. Two different ways. Critical value method versus the p-value method. All right. So I'm going to go down here and we're going to look at a problem or two. All right, I'm gonna go down here. I'm gonna do problem number 11 here, okay? Now it says, using the Z table, which we don't need the Z table because we have our inverse norm table, inverse norm function on our calculator. Find the critical value or values for each. All right, now notice in number 11A, they want us to conduct or find the critical Z values for what type of a test? Is this going to be a one or two-tailed test? What do you think it's going to be if they say a left-tailed test? Is that a one or two-tailed test?
One tail.
One.
All right, so that's just a one-tailed test where the rejection region must lie in the lower tail of the standard normal probability distribution. I'm actually going to draw a picture of my standard normal distribution, and I'm going to show you where the rejection region is. And the size of that rejection region is going to be the size of our level of significance, which is 1%, 0.01. All right, so therefore, to do problem 11, A here, this is your standard normal probability distribution where the mean is 0, standard deviation is equal to 1. This is your rejection region down here, and its size is 1% because that's your level of significance. They want us to find this critical Z value here. So how would we do that? Well, we just use our inverse norm function here. So inverse norm, and the area to the left must be equal to what? 1%, 0.01. The mean of the standard normal distribution is 1, the standard deviation is 0. And then just hit enter. It's that simple. And you'll find your critical Z value. That separates your rejection region from your do not reject the null hypothesis region. So let's see if we can go ahead and do that quickly here. So bring up your calculator. And go grab your inverse norm function. Inverse norm function. And we type in the area 0.01. That's how it would look horizontally if your calculator renders this horizontally. It's always the area to the left of the Z value, always to the left. And negative 2.33. That'd be your critical Z value. Everybody see that there? How we got that critical Z value there? And it would be that value, negative 2.33. That again separates the upper tail rejection of the null hypothesis region from this region down here, which is the do not reject. Okay. So rejection region from the do not reject the null hypothesis region. This value separates the two different regions. And by comparing where your test statistic falls, comparing your test statistic to your critical Z value, you'll be able to determine whether your test statistic falls in the do not reject region or the rejection region. And that therefore will enable you to form your conclusion as to what you're going to do with your hypotheses. All right. That was a lower tail test or left tail test or one tail test. Okay. Now I'm going to do C. We are to find the critical Z values for a two-tailed test. And notice the level of significance we are testing at would be 10%. So for 11C, and I'll draw a picture of this, you're going to have two rejection regions of equal size, one in the upper tail and one in the lower tail. And since alpha was set at 10%, the size of these rejection regions is going to be alpha divided by 2, which is 10% divided by 2, which is 5%. And that's also going to be the size of this lower tail rejection, 5%. Now we can find the critical Z values. So we use our inverse norm function again. And the area is going to be 0.05. And let's find out what those critical Z values will be. That will separate the reject the null hypothesis regions from the region in the middle, which is the do not reject null hypothesis region. Right? So this is the do not reject null hypothesis, and this would be a rejection region, that'd be a rejection region. So we got to find those critical z-values that separate those regions. And to do that, of course, we go get our calculator. So inverse norm time again. And the area to the left of our lower critical z-value is 0.05. Or if you wanted to find your upper critical z-value, you could have typed in the area of what? 0.95, correct? Which would be the area to the left of the upper critical z-value. But I'm just going to use the lower one here. And there you go. You get negative 1.64. So that's your critical z-value, negative 1.64. That'll be this one down here. And by symmetry, this is going to be positive 1.64. So if your test statistic was greater than negative 1.64, but less than positive 1.64, that would lend credence for us deciding to do not reject the null hypothesis. If, on the other hand, our test statistic, which is obtained from sample evidence, is less than negative 1.64 or greater than 1.64, then in that case, we would reject the null hypothesis and opt for the alternative hypothesis as being a truthful statement. Do we understand how we're computing these critical z-values here for whether we're conducting a one-tail or a two-tail test here? Okay. So classwork, you could call it classwork number 1 here. I would like you to do D and E, 11D and E. I want you to compute the critical z-value for D situation and the critical z-values for E situation. We'll call this classwork number 1. Go ahead and do those. Okay, so for 11D, they wanted you to find the critical Z value for a right tail test or upper tail test, where your level of significance is 5%. That means your rejection region of your null hypothesis is going to be in the upper tail of the standard normal distribution, and its size will be 5%, the level of significance. Therefore, to find this critical Z value that separates the upper tail rejection region versus the lower region, which is the do not reject null hypothesis region, use your inverse norm function and type in 0.95 for the area to the left of the Z value. How did I get 0.95? Well, to the right is 5% of the area, so to the left must be 95%. And you would get 1.65. Did anybody get 1.65 for that critical Z value there?
Yep.
All right, now for E, they want you to conduct a two-tailed test. Well, not conduct a two-tailed test. They just want you to find the critical Z values for a two-tailed test where your level of significance is 0.01. So now you're going to have two rejections of equal size, one in the lower tail, one in the upper tail of the standard normal distribution. And the size of these rejection regions is going to be your level of significance alpha divided by 2. So that means we're going to have to take 1% and divide it by 2, which leaves you with an area of 0.005 for the upper tail and lower tail rejection regions. To find the critical Z values, I use my inverse norm and I typed in this area to the left of the lower critical Z value, 0.005, and it gives me negative 2.58. And therefore, by symmetry, then the upper tail rejection critical Z value would be positive 2.58. Did we get these two critical values for that problem? Are we understanding how we're computing these critical Z values here for various tests?
Yep.
All right. Okay, now normal levels of testing again are like what? 1%, 5%, or 10%. But sometimes they have you testing at weird values. For instance, like number 12. I want you also to throw this into classwork 1. Do 12 and D here. They want you to compute the critical Z values for these levels of significance alpha. These are not typical values of level of significance that you would use. But nonetheless, I still want you to find the critical Z values for these two situations. Go ahead and do that. Okay, so for 12D, they wanted us to find the critical Z values for a two-tailed test where alpha is at 2%. And therefore, we're going to have two rejection regions, one in the lower tail and one in the upper tail of the standard normal distribution, the size of which is going to be 2% divided by 2, which is 1%. 1%. Okay. And then to find these critical Z values, I went to my inverse norm function and I typed in an area of 0.01, 0.01 being to the left of my lower critical Z value. And I got negative 2.33. And therefore, by symmetry, the upper critical Z value would be positive 2.33. Did we get those values there?
Yep.
And finally, E, they want us to conduct an upper tail or right tailed. Well, they don't want us to conduct an upper or right tailed test. We're not actually conducting a hypothesis test. We'll be doing that next week. But if we were to conduct an upper tail or right tailed test and we were setting our level of significance, which is the probability of committing a type 1 error at 4%, our rejection region would be found in the upper tail of the standard normal distribution, and its size would be 4%. Therefore, to find this upper critical Z value, I would have to use the area to the left of this critical Z value, which would be 96% of the area of the curve. So I type in 0.96. When I do that, I get a critical Z value of 1.75. Did anybody get that value? $1.75. Anybody?
Yep.
Okay. All right. So hopefully now, ladies and gentlemen, we have a much better understanding, if nothing else, as to at least how to compute critical Z value or values, depending upon what type of test we're conducting, either a lower tail, or left tail test, upper or right tail test, or a two-tail test. Okay. Let's move on to another aspect of our 5-step procedure of hypothesis testing. And that other aspect is going to be problem number 13 here. It says, for each conjecture, state the null and alternative hypotheses that would be tested for such a situation. And I'm going to do A for us, 13A. It says, the average age for a new automobile buyer is 46.7 years. Well, got a question for you, ladies and gentlemen. When you see that statement, the average age for a new automobile buyer is 46.7. Is means what symbol in mathematics? Is. Anybody? Does it mean greater than, less than, or equal to? There's your hand. Which one would it be?
Equal.
Equal to. Okay, look, that being the case, my null hypothesis for number 13A would be saying that the mean age of all automobile buyers out there is equal to 46.7. This would be my null hypothesis. Now, my alternative hypothesis has to be the complementary statement. And what would be the complementary statement? I would say mu is what? What's the other side of the fence?
Less than 46.7.
Well, to say opposite of mu being equal to 46.7, we would say mu is what?
Not equal to.
Not equal to 46.7. Ladies and gentlemen, these would be the hypotheses you'd want to test based on that statement or that claim that was indicated here. Okay. What kind of a test would this be? Upper tail test, lower tail test, or two-tail test? It would be a two-tail test because our alternative statement is not equal to. Okay. All right. That's your answer for that one there. I'm going to do one more. B. The average number of motor vehicles an American family owns is less than 2.8 vehicles. All right. Less than. These words less than mean the symbol less than. So I have a question for you. Does that symbol belong to our null or alternative hypothesis statement? Which one? I know I indicated this in the past. That less than symbol belongs to what statement, the null or the alternative hypothesis?
Is it the alternative?
That's right, it's the alternative. So therefore, you now know your alternative hypothesis statement has to be saying mu, in other words, the average number of vehicles of everybody in the population that they own would be less than 2.8 vehicles. Now, by default, my null hypothesis has to be the complementary statement, which would say mu is what? Well, technically, we would say mu is greater than or equal to what? 2.8. But you know what, ladies and gentlemen, your author doesn't say this. Your author just says mu is equal to 2.8. Okay, but technically, this is the complementary statement of saying not less than. To say not less than means to admit that it's greater than or equal to. But your author is not going to say greater than or equal to. Your author is just going to say this for the null hypothesis. Just equal to. That's it. Just equal to. Okay. Those would be the hypotheses we'd want to test. Now, what kind of a test would this be? Would it be a two-tailed or one-tailed test? And if it's a one-tailed test, would it be a lower or upper tail test?
Lower one tail?
Yep, it's a one-tail, lower tail test, exactly. So your rejection region would be found in the lower tail of the standard normal probability distribution, whose critical Z value would have to be determined by knowing what alpha is, but they didn't specify what level of significance we'd be testing at. So there's no way we can determine what the critical Z value would be unless we specify what alpha is. Okay. All right. Do we understand how we're setting these hypotheses up here? I want you to do 13E, C and D. I want you to set up the hypotheses that these statements would warrant, that we would want to test. Do C and D. We'll call that classwork number 2. All right, let's see if we can maybe take a look at these here and see if you've had any success in setting up the hypotheses that would be tested, warranted by the statement that is put forth. So here we go. Now, number C here says the average cost of books on Amazon is more than $15.28. More than means greater than. So therefore, that would constitute your alternative statement. And your null hypothesis, therefore, would have to, be the complementary statement that says the mean is equal to $15.28. Did anybody get those correct? Those hypotheses.
Yes.
Finally, D, the average number of dogs an American family owns is 1.6. Is means equals. Therefore, that would be our null hypothesis, and our alternative hypothesis would be saying, okay, the mean number of dogs owned is not equal to 1.6. These would be the hypotheses that statement would force us to set up. So hopefully you're starting to realize, ladies and gentlemen, that your alternative hypothesis statement can only be one of three symbols, either less than, strictly greater than, or not equal to. It's got to be one of those three. Okay. That's all there is to it, basically. Once you identify, pretty much your alternative statement, you pretty much have your null hypothesis statement. And notice in all cases here, our null hypothesis statement is always the same. It's always what? Equal to, equal to, equal to. Notice that. Okay. So yeah, your null statement is never going to be less than or greater than or not equal to. It's always just going to be equal to. That's it. So now we're starting to understand how to set up our hypotheses here. And maybe you could just do maybe one more here. All right, so for another classwork here, go ahead, ladies and gentlemen, 14, A, B, C, D, and E. See if you can set up the hypotheses for each one of these here, for each one of these statements here. Okay. I think we're starting to understand this. It's really not that difficult. Just remember, your alternative must always be strictly less than, or strictly greater than, or strictly not equal to. All right, 14, A through E. Go ahead and do those. All right, those would be your solutions to this classwork here. A, B, C, D, and E. Okay, just check those out. How did you fare on those? Notice in each case, your null hypothesis is always equal to. And in each case, notice that your alternative hypothesis is either not equal to, strictly less than, or strictly greater than. Are we starting to understand how to write hypotheses based on statements that are given? Or by hunches or gut feelings or by claims, if you will? Are we starting to understand how to write our hypotheses here?
Yes.
Okay, we're off to a good start. We're learning piece by piece how to conduct hypothesis testing. We're learning each of these 5 little steps kind of like individually here. And by doing that, we're warming up to the whole procedure we'll start to see next week. All right. Okay, let's move on down now to number 17. Now it says for each situation, decide whether the null hypothesis should be rejected. Okay, does anybody remember that little rhyme I put forth regarding the p-value? How did that go for p? How'd that go for p small?
Reject the null.
Reject the null. Exactly. So more specifically, what you want to remember is this. If you compare your p-value with your level of significance alpha, that will enable you to make a decision whether you can or cannot reject your null hypothesis. Just remember, if your level of significance alpha is greater than your p-value, we always reject the null hypothesis. Reject the null. If, on the other hand, that is not true, if your level of significance is smaller than your p-value, in other words, you got a large p-value, you do not reject the null. Okay, and that's all you need to remember. And you're in business. And so these problems really should be quite simple here. All right, how about for like 17a? Would I or would I not reject the null hypothesis? There's alpha and there's your p-value for a particular test. What do you think?
Reject it.
Yes, your level of significance 5% is greater than your p-value, which is about 3.3%. So in this case, because alpha is greater than your p-value, right, we would reject the null hypothesis. And that would be your answer for that one there. Reject the null hypothesis. You see that there? All right, how about for B? What would we do with B?
Accept?
Yeah, we cannot reject the null hypothesis because alpha, which is only 1%, is a little smaller than our p-value. Not by much, but it is. Okay. And because our p-value 0.011 is greater than our level of significance alpha, which is 0.01. Okay, we do not reject the null hypothesis. Okay, so we do not reject the null hypothesis. All right. And so that's basically what's going on here. All right, so ladies and gentlemen, for the let's see here. For the last classwork, just do number 18A through D, and we'll call it quits for today, okay? Do 18A through D. Just indicate whether we can reject the null hypothesis or we do not reject the null hypothesis. And there you go. You can check your results there. That's 18A through D. So it's just a matter of comparing your level of significance with your p-value to make a decision as to whether you are able to reject the null hypothesis or you cannot reject the null hypothesis. Okay. So next week, we'll put this all together, ladies and gentlemen, as we'll actually, get down to business of actually conducting all 5 steps in testing hypotheses for an unknown population mean mu. So you'll see how it all comes together on Monday, okay? But today we were just warming up to the language of hypothesis testing, and we were just doing a couple of the steps, warming up to what we're going to need to do next week when we put it all together with all 5 steps and our ultimate conclusion regarding a particular test. All right, so that's it for today. I will open up the 7.4 homework. And the Chapter 7 exam, I will have to put that together and get that up and running. That'll be due by midnight, November 12th. Just keep in mind that the quiz, Chapter 7, is due by midnight, November 11th, along with your Chapter 7 homework. And with that, I will bid you adieu. Have a great weekend. If there's any questions or concerns or comments, I'll stay on the line for a couple minutes.